this computer. Okay, I think we're recording now. So welcome to Physics 468, which actually is part of Physics 466. For bureaucratic reasons, the department has them, and historical reasons, the department has the two courses listed as separate. If you don't have enough credits to take 468, just take it unofficially because it's going to be part of 466, so we can cover more material. I may be repeating some material here, but I suppose that's not a tragedy. Outer products, the idea basically is that if you have two vectors, you can make what's called an outer product operator. And in the traditional language of mathematics, that operator maps any vector H into the vector F. So it's a projection operator on the vector F, and it multiplies it by a complex number. And the complex number is the inner product of the other vector G with the vector H. So A on H is GH on F. Now, that's a linear operator. What Dirac did was to introduce a notation that made this easier to understand, a much better notation. So if F is a ket represented as a column vector and G is another ket represented as a column vector, then the outer product of F with G looks like this. The inner product of G with F looks like that. And let's see if I have, well, all right, let me throw in a new equation here in, I'm having trouble moving this thing. Hold on. Maybe I need to, yeah, I guess okay, something has, somehow I'm not able to control this. I'm not able to scroll this damn thing. Well, it's made me a totally new screen. So let me try to use it. The basic idea, let's go back to what I was thinking of here, was if F is, what did I write? ABC. And G is ZW, just a two-component object, then FG is, it'll be AAA, BBB, CCC, and then, whoops, yes, no, that's correct. But now this will be Z star, Z star, Z star. Actually, no, I've screwed up. This is wrong. So let me undo the erasing. Let me erase it. So it's, again, ABC. ABC, but now this should be actually a W. Which I hope is what I wrote down. Yes, it's like that. And so then if we have this outer product acting on some vector H, where let us say H is let us say DE, a 2-vector, then this thing will be the matrix product of this structure here, ABC, ABC, Z star, W star, Z star, W star, Z star, W star, times the vector DE. And so that'll be something like a 3-vector, which would be A Z star D plus A W star E, and then B Z star D plus B W star E, and C Z star D plus C W star E, if I haven't screwed it up. So I think I should add an equation to complete this thing on Dirac notation. So F, G, H. Okay, so that's what. Oh, I wanted to get rid of this thing here. Does anybody know how to get rid of this stupid? Well, I guess it'll disappear. So this is the way, this is the notation that Dirac introduced, and it's so convenient that and so intuitive that it has become universal, or should be universal in physics. It's nearly universal. So that's Dirac's notation. And in particular, if you have a complex number times an outer product, well, first of all, the adjoint of a ket is a bra, and the adjoint of a bra is a ket. And similarly, the double adjoint just gets you back to the same thing. Let me remove this if I can. Notice that if you have a, let's see if you have a broad G, an operator C or a matrix C, and a ket F, then you multiply them together to form the word bracket, and they bracket the bra and the ket bracket the operator C. And so that was an additional cleverness that Dirac introduced. The most general linear operator in Dirac's or anybody's notation is a linear combination of outer products, and multiplied by complex numbers. The adjoint is simply the complex conjugates of the coefficients, and then you turn KL into LK. And so the adjoint of a ket H given by A on F, where A is the most general operator, well, that just is this structure here. You get Z star, LF turns into FL, and K, the ket K turns into the bra ket K, and that's F A dagger. So that's the remarkable progress that, well, one of the many, great many things that Dirac introduced. He was truly remarkable. The original expression, the original expansion, where is that expansion? Here's an expansion of an arbitrary ket, arbitrary state in terms of kets where Z's are just complex numbers. So this expansion we can rewrite since CK, these kets we're taking to be orthonormal. And let's see, where did I write that the kets are orthonormal? Well, apparently I didn't write it explicitly. All right, here it is. It's an inline equation. Since the basis vectors are orthonormal, the Elf coefficient here is the inner product of the bra L with the ket F, and that gives you C sub L. And so the original expansion then with CKs is the inner product of K with F, and that's just a number. You can write it this way. Now you can put the brackets around the sum, and you can see that this sum maps the arbitrary state F into itself, and so it must be the identity operator. And of course, it didn't matter which coefficients we chose. The coefficients simply had to match with the kets we were using as an expansion. So if we expand the ket F in terms of basis states alpha sub K or alpha sub J, say, then C sub J will be the inner product of alpha J with the ket F. And we can then see that that just implies that the identity is the sum of the outer products of any orthonormal basis. So the sum of any orthonormal basis forms the identity operator. That's the identity operator is the sum over any orthonormal basis of the outer products of those orthonormal basis vectors. And these resolutions of the identity give you different representations of the ket F. So I'm skipping over the examples, but you should do the examples yourself. And most learning is, or at least half of it is learning done by the student thinking about the subject matter and reading the text, although presumably listening to my lectures is also helpful. So adjoints of operators, well, we've already sort of done that. The adjoint of the basic operator is just the complex conjugate of the coefficient times the interchanged bras and kets, bra and ket. The most general linear operator looks like this. You take the arbitrary operator and put identity operators on both sides. Here I chose the same basis on both sides, but you needn't do that. You could have one basis here and another basis there, and it would still represent the operator. The adjoint then in Dirac notation gives us simply this, and what we can see then is that from the general rule, since L A dagger K has to be equal to K A L star, because of the general rule that I went through before a moment ago, it follows that for any operator, the L-kth matrix element of the adjoint is the complex conjugate of the K-lth matrix element. And so this matrix A dagger is LA dagger K or KAL star, which is AKL star, which is ALK transpose star. So this is in agreement with the previous definition of the adjoint as the transpose of the complex conjugate. We can also write things like this, and in other words, what we can do is if we have an adjoint here, just the meaning of this is the ket F acted on by the operator A dagger, but in Dirac notation that can be written this way. And we've just decided that that's this. And this, of course, is shorthand for that. And that is this. And so in general, then, G A dagger F is F A G star and also all these other things. The adjoint of an adjoint just takes us to Z star and then back to Z, and it flips the bra and ket twice, and so you get back to the same thing. Now, all right, so there are various ways of thinking about that. Now, a special case in physics is that we want some operators to represent physical observables, and what we choose to represent physical observables is the operators that intrinsically give us a real number as an average value or mean value. And so for that, we choose operators that are self-adjoint. And in that case, then AKL is this, but since it's self-adjoint, we can put a dagger there. And then when we take the complex conjugate, everything reverses and the dagger goes away. And that's ALK star and so forth, and eventually a KL, a dagger KL. So the matrix that represents a Hermitian operator is a matrix so that is self-adjoint. That is to say, a matrix that's equal to the adjoint of its, that's equal to its adjoint or equal to the transpose of its complex conjugate. In full Dirac notation with a lot of extra steps here, if the operator is Hermitian, and only if it's Hermitian, you can go through these successive stages. As I said, everything was more, not everything, but many things were more confusing in pre-Dirac notation. So a matrix that's real and symmetric or imaginary and anti-symmetric is automatically Hermitian. I think actually we covered a lot of this last time. So I think that outer product was not the right place to start. A ket is an eigenvector of a linear operator with an eigenvalue if A on the ket gives the eigenvalue on the ket. And what we'll see is that Hermitian operators have real eigenvalues and complete sets of orthonormal eigenvectors. And that's why they're really great for representing representing physical variables. There are also real symmetric linear operators, and you can read that. That's fine. Unitary operators. Unitary operator is one whose adjoint is its inverse. And so U dagger is just U dagger U, which is the identity. And what unitary operators do in physics is they basically change us from one basis to another. And for example, we could have a bunch of basis vectors that represented doing an experiment in one location and then doing an experiment in a different location. We'd expect, because things don't change, or most things don't change when you change your location, or if you're in empty space, presumably nothing changes as you change the location. And so the map from the basis vectors at one place to another in empty space is implemented by a unitary transformation. And moreover, if you have any set of basis, any orthonormal basis composed of kets K and another orthonormal basis composed of kets alpha sub K, then the sum of alpha K, ket, and bra K is a unitary transformation. It's one that takes us from the K basis to the alpha K basis. And you can also verify in these equations that it is, that sum is unitary. Notice there's always the same, and if you have any two bases, they have the same number of orthonormal vectors. And that's was the subject of a section that we did on Tuesday. The sum is just unity, and in fact, you can rewrite alpha K as U on the K, and the same thing for the bra. And then what you have, summing over K, you get the identity, and then U dagger is the identity. So you can go from one identity resolution to the other. And so this is this writes alpha K as UK. We pull out the U and we get the sum over Ks, and that's the identity, and that's U. So there are various ways of seeing it, but the basic thing is that unitary operators take us from one basis to another. And when you compute inner products, they shouldn't change under unitary transformations. And remember that in quantum mechanics, of course, the probability of something, so the P of getting A when you know you have B is the inner product of A with B absolute value squared. And so what we want is that that should be the same if which is, let us call it A prime, B prime squared. So if the A states and the A prime states are related to each other just by doing the experiments in a different place in empty space, or rotating the laboratory in empty space, then these inner products should, these probabilities should be the same. And there are too many automatic things in Apple's. So let me just write this as, so you want that the results of experiments, or the inner products of vectors in the laboratory and the rotated laboratory, or the laboratory and the translated laboratory, to be the same. Translate is physics for move, or move without rotating. This is true, this works out because inner products don't change under unitary transformations. And that's something, again, that Dirac made clearer. Hilbert spaces are basically spaces that are linear vector spaces in which are complete in the sense that every Cauchy or Cauchy sequence is convergent. And there are various examples of that. In one dimension, the set of all squareable functions forms a Hilbert space. Also, in one dimension, one can imagine X prime being representing a particle at position X prime, and X is the operator, X on X prime is X prime on X prime. These states form a basis. It's now orthogonal, but it's not normalized. And the inner product we take to be what we call a delta function. Delta function is actually a functional, and then it maps any function. The delta function null of X prime acting on the function F is the function F evaluated at the point X prime. And in physics, we typically write that as an integral of delta of X minus X prime F of X dx, which is a natural way of writing things because these delta functions occur in Fourier transform integrations and other kinds of integrations. So I'll let you read the rest of that. There's something spooky called antilinear and anti-unitary operators. Their definitions are here, and they only occur in the case of the operator that reverses time. So time reversal is the only example of that. Maybe I should state the properties of it. K on Z times ket Z times ket psi plus W times ket phi gives us Z star K on psi and W star K on phi. And the inner product of K with phi, K phi with K psi is psi phi. So it flips the thing around. And so it's altogether a kind of spooky business. I've never been happy with that notation, frankly. Wigner, back probably in the 40s, maybe even earlier, showed that every symmetry in quantum mechanics can be represented either by an operator U that is linear and unitary, or by an operator K that is anti-linear and anti-unitary. And again, a symmetry is a map of states psi into psi prime that preserves probabilities. So phi prime, psi prime, absolute value squared is phi psi squared. And so the result then is that we represent all sorts of transformations, like translations, rotations, Lorentz transformations, internal symmetry transformations as unitary operators. Determinants. Now, determinants are something which I think we all learned about in high school. So I'm just going to emphasize a couple of aspects of them. I will also admit that determinants to some extent give me the willies because they intrinsically have so many minus signs, and you miss one and everything goes upside down. So I give the basic definitions, and then I want to emphasize that a useful way of writing determinants, rather than just writing an explicit determinant as a matrix with straight lines on both sides, and then doing the multiplication like n squared times. Not really n squared, but almost. Anyway, is to introduce something that I think was introduced by Levi-Civita, but it could have been introduced way before him. Anyway, it's these totally anti-symmetric symbols. So in 2 dimensions, Eij is minus Eji, and so the whole thing can be stated by E12 is 1, E21 is minus 1, and E11 and E22 are 0. And so the matrix, the determinant can be written as Eij times A1i, A2j, or equivalently Eij summed AI1, A2j. And you can also write things this way with a double matrix summing over J, I and J, and then you get EKL times the determinant. Anyway, one useful thing is the area of a parallelogram is the determinant of this particular determinant of the 2 vectors in some sense. You go to 3, nothing changes except that you just have 3 of everything. So you have epsilon, or E, as I should say, E, IJK, where E1, 2, 3 is 1, and then cyclic permutation. So if you move the 1 past the 2, you get a minus sign, but you move it also past the 3, you get 2 minus signs, which is a plus sign. So E1, 2, 3 is E2, 1, 2, 2, 3, 1, and that's equal to E3, 1, 2, moving the 2. And then all the other ones that differ by an odd number of permutations then are equal to -1. Any E symbol that has an index duplicated just is 0. And the determinant then is E IJK, and then this structure here, A I1, J2, K3, and so forth. And this goes on to the minor is, so you learned about this in high school. I'll let you read it and think about it. Laplace apparently, oh, it was Laplace who introduced this before Levi-Civita, then I would say. If you have n, if you're in n dimension, then you have a totally anti-symmetric symbol that's equal to 1. If you, that is to say, E 1, 2, 3 up to n is equal to 1, and then it's totally anti-symmetric, so that defines all the others. And the determinant of an n by n matrix then is given by this sum over all n rows or equivalently columns. I'm going to skip some of this because you can take forever to do that. If you take the determinant of the transpose, you're just putting a I11 turns into 1 I1, but that's already a formula that we saw was equal to the determinant. So the determinant of the transpose is equal to the transpose determinants. What's also true is that if you multiply a multiple of one column and add it to another column, the determinant's unchanged, and the same thing with rows. And that what follows then is that if you have an n by n matrix whose rows or columns are linearly dependent, then the determinant vanishes because you can take a linear combination of the columns and get 0. And so you can make one of the rows 0 and or one of the columns 0. So determinant of any matrix whose columns or rows are linearly dependent must vanish. So here, what I sort of was skipping over, if we go back to Laplace's expansion of the determinant in terms of the matrix elements together with the minors. Let me see. I actually don't remember if they're the cofactors. Okay, the cofactor is the cofactor. Well, first of all, M is the matrix with the ith row and kth column removed, and then you multiply by -1 to the I plus k. That's the cofactor, and then you take that cofactor and transpose it, divide by the determinant, and that's the inverse. And here then is a proof of that. So that's the formula for the inverse of a matrix. Notice then that the inverse of a matrix is 1 over the determinant. And so the determinant, if the determinant is 0, the matrix has no inverse. And we say that a matrix that has 0 as its determinant is singular. And so every non-singular matrix has a determinant. And what you do is the inverse then has a non-zero determinant if it's non-singular. And if it's non-singular, then you take the transpose of its cofactors, divide by the determinant, you get the inverse of the matrix. And so in particular, A inverse is 1 over the determinant and then the transpose of the matrix. The transpose of the cofactor. So it's the transpose of the cofactors, not the transpose of the matrix. That's why the D jumps up to first place here. And what you can also, what is actually proven here, and I urge you to work through it if you haven't recently had a course on determinants. The determinant, if you have two matrices, the determinant of one matrix A times the determinant of another matrix B is the determinant of the product of the two matrices. And here's actually just an example of that. And in general, then the determinant of the product A through Z is the product of the determinants. In terms of the identity matrix is 1, and that can be written as AA inverse, and that's the determinant of A times determinant of A inverse. So the determinant of A inverse is 1 over the determinant of the matrix. Okay, we're supposed to go to 6:20, and so we've got about 15 or 16 minutes left. Here's an example that's actually worth doing, because you might not have seen this. We've seen the formula for the determinant. So the partial of the determinant with respect to a matrix element is the cofactor. So that's another sort of obscure way of defining the cofactor. But then that means that if you take the derivative, suppose these cofactors and so forth depend upon some parameter beta, then if you take the derivative of the logarithm of the determinant, well, derivative of the log is 1 over the determinant. And then you have the derivative of the determinant with respect to the matrix element times the derivative of the matrix element times the parameter. But the derivative of the determinant with respect to a matrix element is just the cofactor. And we bring in the determinant, so we have this structure here. On the other hand, this is the inverse. And now we see we're summing over I and K. So this is the trace of A inverse times the derivative of A with respect to beta. All right, so this is an important formula. I remember when I was a graduate student, first year graduate student, I had never learned this formula in college. And Schwinger was lecturing, and he just said, and of course, the variation of the logarithm of the determinant of X is the trace of X inverse variation X. And I wrote that down studiously, and then understood it eventually. So I'm giving you the benefit of proof of the thing. So there are, I think we can skip those parts there. There's something called the LU decomposition, and it's you can factor a square matrix into the product of a lower triangular matrix and an upper triangular matrix. So that's called the LU decomposition. MATLAB uses that a lot. Jacobians. Now, the Jacobian is basically a determinant. All right, let us just define it. The Jacobian is the determinant of the partial derivatives. So you have basically, let us see here. We have y as a function of x. And so the Jacobian of x with respect to y is the partial of the x's with respect to the y. So this is where the x's are functions of y. And then if you look at two integrals, you're integrating over a region in x space, and then you change it to an integral over y. The way to change that is to use the absolute value of the Jacobian to convert you from dy1, dy2 to dx1, dx2. And then f of x is just f of x of y. And so that's your formula. In other words, you just write this here as a function of y. You write f of x as a function f prime of y or fox of y times the Jacobian. And that's how you get from one integral to another. If you're in 3 dimensions, the integral over x is the integral over y times the Jacobian that takes you from d cubed y to d cubed x. And so basically it's the d cubed x is this, d cubed y is that, and d cubed x is the absolute value of the Jacobian times d cubed y. In n dimensions, it's the integral of f over all the n's is the integral of f of y times the absolute value of the Jacobian times dny. And okay, there's also something called the Hessian, and I just skip that. Systems of linear equations. Suppose you want to solve this. Well, if you have, if I runs from 1 to n and k runs from 1 to n and a is non-singular, bingo, you just write this as, here, maybe I should say that in this case, you just have y is equal to a of x, and so x is equal to a inverse y, and so you're basically done immediately as long as a has a non-zero determinant. On the other hand, there are two other possibilities. One is that you might have fewer than n equations, so you only have to solve this for I equals 1 to m, whereas this matrix, whereas you have n x's. And so then the situation is underdetermined, and you always have solutions, but they're not unique. So your solutions will depend upon a set of parameters. And so let me write that down. There's a way of dealing with the other case, because let's see, did I mention the other case? The other case is where you have more equations than variables, x, and then you, in general, can't solve the equations unless A is singular and has a zero determinant. So in the case where you have more equations than you have variables, the problem's overdetermined, you have no actual solution. But what you have is something that Gauss invented, which is a way of getting good guesses for the solution, or best approximations. And what you do is you write down what your error is. Your error is going to be yi minus your guess squared, summed I equals 1 to m, where m in this case exceeds n. So you only have n parameters to choose, and you need to fit a larger number of y's. So you sum up your squared errors, and now you want to minimize this. Well, the usual way of minimizing something is to set its derivative with respect to the independent parameters equal to 0. And that gives us this equation here. Partial E, partial XL equals 0 gives us this. And massaging that equation in fact is A transpose Y is A transpose X, A transpose AX. And what you do is you multiply both sides by A, and then you realize that AA transpose typically is positive, or A transpose A is typically, you don't multiply, you just take this equation, A transpose A is non-negative, and if it's also positive, then it has an inverse, and so you take the inverse of it, and you get X. So in most cases, this works. On the other hand, if some of the if this thing has a 0, then a 0 eigenvalue, this is a hermitian matrix. If it has a 0 eigenvalue, then you can't take the inverse. But if A transpose A is positive, as opposed to just being positive definite, then as opposed to just being non-negative, say, then this gives you a good guess. This is Gauss's guess, and it's hard to do better than Gauss. If you're in complex land, then the analogous equation is A dagger A inverse times A dagger Y. And these things, A transpose A inverse, A transpose, and A dagger A inverse, A dagger are what are called pseudo inverses. And they're discussed in a later section. Lagrange multipliers. Whoops, sorry about that. The maxima and minima of a function are among the points at which the gradient vanishes. These are the stationary points of a function f. But on the other hand, what if you want to find the extrema of the function f of x, where x is not, where you're restricted to a subset of all this, of the whole vector space x, in which x is an element. And so what we do is we use Lagrange multipliers. If there's one constraint, c of x equals 0, then we need the gradient to vanish only in those directions dx that preserve the constraint. So what we have as a condition is actually that dx dot grad f is 0 for all dx such that dx dot grad c is 0. And so the extrema of x subject to the constraint satisfy these equations. C of x is 0, that's the constraint. And then the grad of f is proportional to the grad of c. If you satisfy these two, then you found the extrema that satisfy the constraints. And these then are n equations here plus 1, they're n plus 1 equations. These are actually the extrema of the unconstrained function. So we define a new function, f of x minus lambda c of x. And now we require that all the derivatives of this vanish. And the derivative with respect to lambda is just the constraint equation that c of x vanish. And the other equations are the ones that you solve in order to find the x that makes f extremal while satisfying the constraint. If you have lots of constraints, then grad f must vanish in directions that preserve all of the constraints. And so what you have is that the gradient will satisfy, the gradient will dot into dx and give 0 if they are a linear combination of the gradients of the constraints. Let's see, I don't think I made that very clear. What we need is to have the derivatives of f vanish for dx's in the direction such that all of the constraints are maintained. And so what one has then is k constraint equations and then one general function, which is f minus independent parameters lambda, which are called Lagrange multipliers, times the constraint functions. And then what you do is you require that the derivative of L with respect to all the x's and all the lambdas vanish. And the derivative with respect to the lambdas give us back the constraint equations. And then these are the equations we solve for x. And like that. And let me do this example, which I find actually quite amusing because it illuminates something that you might have wondered about when studying quantum mechanics. Suppose you want to find the extreme of a real symmetric quadratic form, x transpose ax, subject to the constraint that x is a unit vector. Well, then you write down your constraint, x dot x minus 1. We want that to be 0, so we write that as minus lambda. And then here we have L as x transpose AX. Taking the derivatives, we get this equation. And then this is the constraint equation following from the derivative of L with respect to lambda vanishing. And the extrema then are, this thing is the eigenvector equation, and this is the normalization equation. So you see, that's where all of that comes from in quantum mechanics, why it is that we're looking for the eigenvectors of Hermitian operators. And it's we require our states necessarily to be normalized. If the states are normalized, then the way in which the average value of an operator is extremal in that state is that the state should be an eigenvector of the operator with an eigenvalue and that the state be normalized. So that's how those things came about in quantum mechanics, why it is that in quantum mechanics, we're always talking about Hermitian operators, orthonormal vectors, and eigenvectors of the Hermitian operators. Okay, so I'm just to make sure that and to teach you a tiny bit of useless, it's not the most useful bit of LaTeX, but it's a little bit of LaTeX. So let me just put here text. We stopped here. And whoops. So in my text file, I'm going to write it this way, TCR, and let me recompile it. Okay, so now I will know where we stopped. I actually did something but then last time, but then erased it. All right, so I hope see you guys tomorrow at 5 o'clock. Thursday, the class is at Tuesday, Thursday, it's at 5, Wednesday's at 5:30. The class on Tuesday, Thursday lasts an hour and 15 minutes. The class on Wednesdays lasts 50 minutes. And but I can hang around for questions. There hasn't been a question so far, so I mean, I realize that it's hard to ask questions. It's probably easier to answer questions than it is to ask questions, paradoxically. Anyway, I'll hang around for a few minutes while maybe I'll stop recording. So anybody who, all right, so I'm going to stop recording.